Good morning. It's the biggest class there's ever been of space vehicle dynamics. So I'm here in the woods, as you can see. You could call me Dr. Ross. Let me give you some background so you know who's going to be teaching you this stuff. So I am from California. I was born and raised there, specifically Southern California. Anaheim, if you know Anaheim, that's where Disneyland is. So I grew up 2 miles from Disneyland. And I got sick of Disneyland, so. But I liked space. So when I was a kid, the space shuttle was a big thing. Like there was a shuttle. I even have a little toy. Check this out, shuttle. It was, and initially it had nowhere to shuttle to, which is kind of weird. It was just shuttling to space. I think the idea was there would be a space station and it would shuttle there. But for like 2 decades, there was no space station. And then they built the space station and it's been there for a while now. So I thought, oh, I want to be an astronaut. Probably many of you thought the same. I went to DC, even though I lived in California. And some kids want to go to the Air and Space Museum. I just wanted to stand in front of NASA headquarters. No, I don't know. I think I'm 9 or 10 years old. I had an aunt and uncle that live in Reston, Virginia. They still do. So got to visit DC a few times. Here's little nerd Shane standing in front of his solar system poster. And I'm wearing this shirt 2010. That's when 2010 was like way in the future. Like, whoa, we're going to have spaceships and humans going to Jupiter on a regular basis. That's what I thought. Didn't happen. I also didn't anticipate the internet. So I got interested in physics. I went to college, took physics. I was a physics bachelor student. I almost failed my first physics class, by the way, like almost failed. And when I barely knew calculus, I applied for a research experience for undergraduate with a NASA mathematician working on solar system dynamics. I was really interested in like, oh, how do they design trajectories for NASA? They must use relativity or something. And no, they don't. It's just Newton's laws. But I worked with a NASA guy at the Jet Propulsion Lab, JPL. And apparently I like standing in front of posters. So here's me presenting the work to a couple of cool dudes. In 1997, I'm still a college student actually at this point, but there's interest by NASA in our work. We were doing things related to Lagrange points, and I'll say a little bit about that to give you an idea, the points of balance in the 3-body problem. And you can design what are called low energy interplanetary transfers. So this isn't just swing bys, it's something different. When I graduated with my bachelor's in 1998, I was just tired of school, just tired of it. Other friends were getting jobs or going to grad school. I'm like, I'm out. I am out. So I went off to take a hike in the mountains, solo hiking on the Pacific Crest Trail. So the Pacific Crest Trail is this like 2,600-mile trail that goes from Mexico to Canada. And I did not do the whole thing. I went from the middle of Oregon to the middle of Washington. So yeah, eventually I looked like that, grew a giant beard. That was a lot of fun. And then I had my head cleared. So then I was ready. I worked at, I got a position at JPL for a year. And then from 99 to 2004, I worked on the same topic of designing interplanetary trajectories in graduate school. And I worked with a mathematician, Gerald Marsden. He's my PhD advisor. He's written some books on calculus and other things related to math. So I got my PhD. There's my dissertation, graduated, and eventually wrote a book on designing space missions using these methods, which is free, by the way. It's on my website. You can Google it. One of the main motivators for what I did for my PhD was this mission called the Genesis mission, which maybe you heard of. It's probably launched before you were born. I don't know. But this was a solar wind sample return mission. So each of these, I don't know if this will work. Ooh, cool. It has these, they were aerogel kind of bicycle tire sized samplers that were going to open up in space and sample the solar wind. So particles, there's high energy, particles shooting out of the sun. We get protected from them on Earth by the magnetic field. But if you could go far enough out, then you could collect these things, close up the capsule, and then bring it back to Earth. And that was the idea behind the Genesis Discovery mission. So to get far enough away from the Earth and to have like a constant view of the sun, there's this point called L1 that's in the direction of the sun. It's on the line joining the sun and the Earth, about 1 million miles towards the sun, or 1.5 million kilometers, because we're metric and all that. So that's far enough that you're outside of the magnetosphere of the Earth, and you can get a direct view of the sun. So if you don't know about these Lagrange points, think of the sun and the Earth, and in a frame, in a frame that's moving around with the Earth, there are 5 points of balance. 2 of them are stable, L4 and L5. L4 is 60 degrees ahead of the Earth's orbit and along the Earth's orbit. If you put something there, it'll tend to stay there. And L5 is 60 degrees behind. You put something there, it'll stay there. And then there are these other ones called L1, L2, and L3. They're unstable. So if you start with something there, it eventually just sort of drifts off. And it might drift off towards the sun, or it might drift off towards the Earth. And L1 was the one chosen by these Genesis mission designers. I came in later in the process, so I didn't pick where it was going to go. And just to give you an idea of why do these points of balance arise, intuitively think of gravity as being something like this funnel thing that you see at science museums. You put in a quarter and the quarter will sort of go around. Well, that's kind of what's happening. That's what orbits are. So if this is the gravity well of the sun, then orbits will just sort of circle around, right? Now, if you have a deep gravity well and then something smaller, so this one, deep one's the sun, this other one's the Earth, then there's actually, on either side of the Earth, there's these points of balance in this rotating frame. So they get dragged around with the Earth. And if you're right there, then gravity and forces due to the rotation, so centrifugal force, balance out. L1 kind of makes sense. The one in between the two, L2 makes less sense, but it is there. And not only are these points of balance, but you could have orbits about these points of balance. Now that's really weird. They're unstable orbits, so if you're a little bit away from it, you drift away. But they have a pretty large time constant. So an orbit around the sun, Earth, L1 or L2 takes about 6 months. It's half a year. So this was the Genesis sample return mission trajectory. It has different phases. So the rocket launches, leaves the Earth, and then there's this green transfer trajectory to this thing called a halo orbit. So the yellow part's called halo orbit, because as seen from Earth, looking out at the sun, it looks like there's a halo, some ring around the sun. And so this is one of these orbits around this X here is the L1 point, and then the sun is about 90 million miles to the left. So this, like I said, this orbit was about 6 months. So this spacecraft spent 4 orbits or 2 years, sampling the solar wind, and then it left that orbit and came back, has this large looping return portion, because it was important to arrive on the daylight side of the Earth. And the only way to do that is to approach from the opposite side. The interesting thing about this trajectory is that it required, once you leave the Earth, it required no fuel. It's a natural trajectory of the system. So that's what was pretty amazing about it. It required no fuel if the rocket does everything just right, which rockets don't do that. So yeah, this just sort of summarizes. It was to gather solar wind samples, return them to Earth for analysis, returning into the Utah desert during the daytime. So the capsule would close up, return to Earth, and a parachute would deploy. And then the capsule would be falling slowly to the Earth. And while it's in the air, a helicopter would come and snatch it. So this is showing, this isn't the actual Genesis capsule being brought back. Apparently, the US government, for purposes that I do not quite understand, had done this hundreds of times for other things. I don't know. But they had good practice. So this is a way of, like, why not just let it come to the, if you want to make it come down as gently as possible, you snatch it in midair, and then the helicopter lowers it as slow as you want back to the Earth. So the Genesis launch was August 8th, 2001. I'm guessing this is kind of near when you were born, for many of you. The launch went great, but when you don't know how well the launch is going to go, and when I say the launch went great, I mean it imparted the correct delta V, right? It gave it the right change in velocity so that it was on the correct trajectory. But often rockets, they have ratings on how much of an error they'll induce. And sometimes it can be pretty large, like 1% error, which if you're talking about 3,000 meters per second imparted, if you're off by 1%, that's 30 meters per second. And for a trajectory like this, you want to be on the correct path. So part of what my work was calculating optimal trajectory correction maneuvers, TCMs, so that if you had some error, you could actually get on the correct trajectory. So what I'm going to show here in several different views of the same trajectory, the red trajectory you'll see is the halo orbit at the right phasing that we're trying to get onto. So you could think of it as the blue thing is our spacecraft, and we're trying to rendezvous with this virtual point, because it was very important that the timing be correct. And we calculated trajectory correction maneuvers in the case of an error imparted by the rocket. But the rocket actually did pretty well, so yay. That's good news. And this is in a regime of the dynamics, orbital dynamics, that's chaotic. You often don't think of orbital dynamics as being chaotic, but for this case, it was. So what we're looking at here, there's the Earth in the middle, you've got the lunar orbit. The Genesis, I said it was called a halo orbit. Genesis halo orbit is shown here on the left. And then these green things are many different trajectories. So if you impart the smallest little delta V, even like 2 meters per second or something, so you turn on your rocket for a microsecond or something, it's very sensitive. So the return trajectory, if you were off by a little bit, you could have trajectories going all different places. And then there's one special trajectory here, that's the return trajectory. And so it makes this big loop, and then it returns on the left side of the Earth here is the sunny side. And we wanted to arrive in Utah, in the desert, in daylight, which we did. So Genesis returned September 8th, 2004. And the helicopter was ready. But this is not actually what happened. This is not a photo from that event. So the helicopter was ready. But as often happens in complicated engineering situations, something went wrong, something unexpected. So a parachute was supposed to deploy. A parachute did not deploy. So this thing was coming in exactly where it's supposed to be landing in the Utah desert, but no parachute. Eventually, it was found out that the parachute deployment explosive was put in backwards. So I don't know, somebody got fired maybe. And so this is what actually happened. The capsule, it looks like a hamburger, right? It's coming in at, yeah, it just slams in at 100 miles per hour. So it reaches terminal velocity. I mean, the trajectory designer, you know, we did the right thing. It landed where it was supposed to land, and it made a big crater. Yeah, whoops. They were able to retrieve some of the solar wind samples. They did, you know, kind of expect maybe this could happen, but not due to human error. So yeah, as they found out later, it was human error. Parachute explosive thing put in backwards. So wasn't someone from Virginia Tech. Okay. All right. What's another thing? Yeah, this just gives you another idea of what these points of balance can do. This is a comet. It's a comet called Oterma from 1910 to 1980. On the left, I'm going to start this video. It'll show the comet with the sun in the middle, and then we're showing Jupiter in its orbit. On the right, we're jumping into what's called the Sun-Jupiter rotating frame. And you know, rotating frames are going to play a big role in this class, not necessarily for trajectory design, but for rigid body dynamics. And so it's as if you have a camera high above the solar system, above the sun, and that camera is rotating at just the right rate so that Jupiter is always along the x-axis, right? So it's slowly rotating. And you can see what this comet does. Oops, let me go back. I think it'll work. There we go. Yeah, there's the comet. It passes by Jupiter. So on the left, you see kind of the usual picture that you're probably used to seeing. On the right, it looks totally crazy. Like, what's going on in this rotating frame? I don't get it at all. So you kind of have to stare at it a little bit. So this comet comes close to Jupiter, near these L1 and L2 points of the Sun-Jupiter system, and has this little excursion inside, got closer to Jupiter, closer to the sun, and then it goes back outside. And there's actually a whole class of comets that do this. Some of them end up crashing into Jupiter. So before year 2000, in 1994, a comet Shoemaker-Levy 9 actually crashed into Jupiter, and it's in this sort of same category. They are among the most chaotic objects in the solar system. Like, I don't know what's going to happen to Oterma. Nobody even knows where it came from. Something's bound to go wrong eventually with that comet. All right, the last, I guess, no, this is the last one. Another trajectory design thing I worked on was a mission to Jupiter's moons. And Jupiter has these, so it's the 4 Galilean moons. It's the moons that you could see if you have binoculars going around Jupiter. And they are, at least 3 of them are thought to have perhaps liquid oceans underneath it. So Io, the one closest to Jupiter, has volcanoes, which is cool enough. Europa is the most likely to have an ocean underneath and thick layer of ice, and then probably the same for Ganymede and Callisto. And so you can see their size compared to the Earth and Moon. So this is what Europa is thought to look like. I don't know how thick they think the ice is. It could be a mile. And underneath is liquid ocean. And you might be saying, well, wait, this is so far from the sun. Why is there a liquid ocean? It's tidal heating due to being so close to Jupiter's gravity field that heats these things up. And it's thought there could be, I don't know, like 100-kilometer deep ocean, which is kind of crazy. So whereas we have lava and mantle, these things have liquid water, and they can erupt and create, liquid water, volcanic eruptions. So this is just an artist's picture of, one day, perhaps one of you will work on a mission where you land on Europa, drill through, and then there's some kind of ocean explorer that discovers something. That'd be awesome. Hasn't happened yet. The first thing would be, you got to map out the surface. So this is a video just showing a spacecraft that's in orbit around Europa, kind of mapping the surface, looking for maybe the best points of entry to get into that liquid ocean. So it's using remote sensing instruments to map out the surface, see how thick the ice is, and then transmit that back to Earth. So, interplanetary missions are like an order of magnitude harder or more than missions around Earth. But they're very exciting. So all this stuff about, finding low energy trajectories around the solar system. This is another artist's picture, but it's been called the interplanetary superhighway or interplanetary transport network. So if you want to know more about it, you can Google that. One thing that we worked on was designing a mission that could orbit each of the moons of Jupiter. And this is sort of a picture of if you get into orbit around Jupiter, then you could eventually orbit each of these moons if you do kind of cleverly timed trajectory maneuvers. So this is showing the red is the spacecraft, and it first did a flyby of Ganymede, and then after a delta V gets captured by Europa. And this sort of shows what it looks like. And that the final approach to Europa, you have this weird corkscrew looking situation because of the three-body dynamics. And then if you do a delta V, you get injected onto a highly inclined orbit and kind of map out what the surface of Europa looks like. So eventually there will be a mission like that. Juno is not that mission. Eventually there will be something like a Jupiter icy moon orbiter, but not yet. All right, closer to home, Earth-Moon system. There's a lot of interest in doing stuff at the moon. And we designed a trajectory that gets captured. This isn't for a manned flight. This would be like a unmanned thing. You actually use, this is strange, the sun's gravity to get captured around the moon using less fuel than an Apollo-like transfer. So it uses 20% less fuel. It takes 6 months. I mean, if I show that video again, you'll see the moon is going around a few times. So you're trading fuel for time, and yeah. So there's all these techniques that have been worked on now for these kind of strange looking low energy trajectory, and they're usually related to Lagrange points, which is a cool subject in and of itself. Anyway, in 2006, so I was a postdoc. Actually, I worked at Boeing as a consultant they were trying to win a bid for an interplanetary mission in 2004. So I worked for Boeing in El Segundo, California. Was a postdoc at University of Southern California for 2 years, and then I joined Virginia Tech Faculty of Engineering. 2019, I joined the Aerospace and Ocean Engineering Department. So now you know a little bit about me. What's the goal of this course? Okay, it's to introduce you, basically, it's to introduce you to 3D rigid body dynamics in the context of spacecraft attitude dynamics and control. And that's a good thing. So spacecraft, and I have a little, so one of my sons really likes Lego. So I said, hey, can you make me a spacecraft? And don't get too fancy. So he made a box with an antenna. I think that's what they are anyway, most of them. So here's a box with an antenna. And when this thing's out in space, right, you want it to point the correct direction. I'm not sure what the going rate is for putting something into low Earth orbit. I think with the Falcon 9, it's like $3,000 per kilogram to get something into low Earth orbit, which is a big improvement over back in the space shuttle days. It was like $50,000 per kilogram, which is the price of gold. So now 3,000 per kilogram, just to give you the basis of comparison. Got some CBD oil here. So that's about the price of CBD oil, if you think of it per kilogram. It's kind of weird. So spacecraft are often, a typical size is like 500 kilograms. So we're talking tens of millions of dollars, and you want these things to do the right thing, right? Once you get them into space, their main thing is to do remote sensing and communications. So they need to be oriented correctly to be able to achieve those goals. So 3D rigid body kinematics and dynamics are very important for spacecraft. It's also important for other things, aircraft, boats, other vehicles. In fact, 3D rigid body kinematics and dynamics are important now in computer vision and video games. So the skills that you'll learn here could transfer to other things if necessary, but we'll be looking at the application of space because space is cool. Plus, arguably, space vehicles have the largest domain to wander because space is so big. So take that, aircraft. The catalog description is the catalog description. Here's the textbook. So this is largely going to be based on my notes, but there's also a required book, Analytical Mechanics, Space Systems. I've got it here. It's 4th edition, okay, 2018. It's in the bookstore. It's written by Hans-Peter Schaub and John Junkins. I know these two. John Junkins is at Texas A&M, and he's a nice guy. And one of his PhD students was Hans-Peter Schaub, who was actually at Virginia Tech until about 2007, and then went to University of Colorado. So they wrote this book, and I think we're mostly just going to be looking at the first 4 chapters. There's other books that which is like half the book. There's other books that take too long. I would rather stick with the keep it simple principle. So I'm going to try to keep it simple and give you intuition as much as we can. There's other textbooks that are not required but might be useful. So this one is listed right there, Engineering Dynamics by Kasdan and Paley. They're also from aerospace and mechanical engineering departments. And they use some very similar notation, but I will be sticking with the notation of this book. They're very careful about writing the kinematics because that is foundational. And then there's this other book, Principles of Dynamics by Greenwood. I don't have a copy of it here. It's probably in my office. And why look at the other books? Because they have lots of worked examples. Okay. In this class, I'll be trying to give you theory and also working through examples because that's really useful. Here are the topics that we're going to cover. There'll be probably next time, be some motivation on mission analysis and the requirements for pointing, just so that, why are we doing this? But then we'll go into more of the theory about kinematics for a single particle and reference frames, then dynamics of a single particle. We're going to kind of build up to rigid bodies by talking about multi-particle systems. And then if you have a multi-particle system where all the particles are rigidly attached, that's a rigid body. And then you can think of a continuous mass system. So we'll talk about rigid body kinematics. And then that's just describing the orientation of a rigid body. Right, here's a rigid body. And it basically comes down to attaching a frame. Look at this cool triad of vectors that I made and painted. Yes. All right, so you're trying to describe how these three vectors that describe a frame attached to your body, how do they change with respect to another frame, an inertial frame? And that'll be a big part of what we do. And then eventually, once you have some dynamic equations, you can solve these analytically in simple cases or special cases. And then there's constants of motion, like energy and momentum. And that's all good. All right. So covering those topics above, you should be able to do the following. You'll be able to understand inertial and rotating reference frames and how they relate to particle kinematics, and then use Newton's laws to derive equations of motion for particles. Rigid body dynamics, or for spacecraft, the terminology seems to be attitude dynamics. So derive and explain the motions of rigid bodies. And even before that, there's rigid body kinematics that describes the orientation of the rigid body. And a big part of that will be rotation matrices, and then other ways of writing a rotation matrix in terms of angles and quaternions. And then we get into some, how do you determine the attitude of something? So there'll be different measurements because there's sensors on board. Our phones, all our phones have like tons of sensors. Right, your phone knows where it is with respect to the inertial frame, so your satellite should. There's spin behavior and stability. So there's the static, the uncontrolled dynamics of a satellite is what we're talking about here. If you have a rigid body, are there directions in which it could rotate where it's stable? Spacecraft attitude dynamics, that just means taking attitude dynamics and looking at the environment that a spacecraft is in. So environmental forces, well, what's the environment base? Well, there could be a little bit of drag. There's also, if you have a large enough body, then the gravity closer to Earth is stronger than the gravity further from Earth, and you could use that to your advantage. There's also the magnetic field of the Earth. So we'll talk about that. And then how to do control, some ideas about controlling. If you've got thrusters, you could turn something, or you could use momentum wheels. And those are less intuitive, but they're there. This is what most of the class is going to look like. I'm going to be on OneNote with graph paper in the background. So it helps me draw straight because I don't draw too straight. So let's just dive on in, okay? So the spacecraft attitude. So this is just in sense of the terminology, the orientation of a spacecraft. Is called its attitude. Right. By orientation, we mean like the 3D orientation. So here's the spacecraft in front of the camera. It's a Lego thing. Right. And spacecrafts have instruments and antennas on them that have to be pointed in specific directions. Right. There's often instruments and antennas. Have to be pointed in specific directions. Always within some tolerance. So, for example, the Hubble Space Telescope needs to point the telescope part, the mirror. has to point in the correct direction. The Hubble Space Telescope also has the additional issue that it has to look at that thing and stay steady. Otherwise, the image will be blurred. It's like when you hold your camera and shake it. And then communication satellites have to point their antennas. And now there's all this talk about like giant constellations of communication satellites so that you could have internet access, anywhere in the world, thanks to spacecraft. What about control? So to control the attitude, spacecraft operators, which could be the spacecraft's own computers. They must be able to determine the current attitude. Right, that's where sensors come in. And then determine the error between that current attitude and the desired attitude. I kind of don't like calling it error. We just mean the difference between where you are currently pointing and where you want to point. And once that's been determined, you know, how do you have to turn? Well, you have to figure out how you have to turn first, and then you would apply control torques. I might also refer to torques as moments. So anytime I just use a different phrase, I'll put AKA, also known as moments, control moments, to reduce error to 0 or close to 0, right? Nothing's perfect. Sensors always have noise. Actuators don't do things perfectly. Sometimes the charge for the parachute gets put in backwards. No, we don't. Totally unrelated. All right, so that's just kind of, you know, broad. You've got the spacecraft, it's pointing in a certain direction. You want to point, oh, I have another vector. I've got a bunch of these little vectors. I want to point this way, and I'm pointing this way. So now I figure out, okay, I need to go that way. There are, I guess I'll just tell you, there are coordinates that can describe the orientation of a rigid body with respect to a reference frame. And these are attitude coordinates. And there's different choices of them. We'll spend a lot of time talking about, well, what should we use? So these are coordinates that completely describe the orientation of a rigid body with respect to a reference frame. And by the way, I often do not use PowerPoint slides because I've noticed sometimes I would blast through them quickly, whereas if I slowly write it out, you can see it. Plus, when I do work examples, I think it's much better for you to see me write it out. And for your own learning, it's probably good for you to take notes. Even though this will be provided, it's good for you to take your own notes. So to define the attitude coordinates, we have to select two frames. So there's a question, do I give recommended readings from the book to follow along with the lectures? Yes, typically, but this stuff is not in the book. They don't really give like a high level, here's why we're gonna do this. Yeah, so if you look at chapter 1, it kind of dives into particle dynamics. So unfortunately, this isn't in the book, but yeah, I will try to give you, where to read in the book. So to define the to define the attitude dynamics, the attitude coordinates, we must select two frames. One is the frame to which the orientation is desired. So for example, an inertial reference frame. So I'm going to use the example of, here's an inertial reference frame, and I'll often actually use red vectors because I have this red thing. So if this is my inertial reference frame and I've got a satellite will need to do something. I want this to be oriented in some way with respect to this inertially fixed reference frame. So this first thing would be like the inertial reference frame. The other one needs to be a frame attached to the body. Attached to the body. Often called a body fixed reference frame. Okay, so if this is my rigid body, it's a satellite, I would attach a frame to it. And it's like, this frame is attached to the body. So now I can kind of abstract away. I can take the body away and it's just, okay, I have this is a body fixed frame. And how do I describe the orientation of this blue frame? I keep calling it a frame. It's a triad of unit vectors that describe a right-handed coordinate system. One is attached to the body, one is the inertial frame. How do I describe the orientation of these two? Well, that's what attitude coordinates are. So attitude coordinates relate these two frames. Okay. And just some points that maybe aren't obvious. And we will go into more detail about this later. You need at least 3 coordinates to describe the orientation between 2 frames. So that means that you need 3 numbers. So you need at least 3 numbers, and maybe it's not obvious, but just to roughly tell you, what do these 3 numbers mean? We got these 2 frames. If I want to describe like an arbitrary orientation of one frame compared to another, I can do a series of 3 rotations about primary axes. So I would rotate a certain angle through one, and then a certain angle through other, a certain angle through the other. So 3 numbers. So there's these are called Euler angles, the typical ones that you've probably heard of, and they're just one set among many, are yaw, pitch, and roll. Okay, so maybe have that in mind. Like here's my space shuttle. I've got yaw, I've got pitch, I've got roll. And then if you combine those, like a yaw, a pitch, and a roll, you can define an arbitrary orientation of the space shuttle compared to an inertial frame. Now, the problem with using just 3 coordinates is that if you only have 3, there's going to be at least one orientation where the coordinates are called singular. So if only 3 coordinates are used, this can lead to problems. And that's why, even though they're nice for explaining things, they're often not the ones that are actually used for spacecraft. What is this problem? There will be at least one orientation where coordinates are singular. You know, be okay, what does that mean? That means, okay, 2 coordinates are undefined or not unique. I mean, in general, just think of singular as bad. The singularity, the middle of a black hole, you don't want that to happen to you. All right, so at those orientations, these problematic or singular orientations, there are some differential equations that also lead to problems. So people have come up with sets of 4 coordinates. For example, things called Quaternions, and there's others. There are sets of 4 coordinates that exist which do not contain singularity, so they don't have this problem. And maybe you're asking, like, who cares? If you've ever seen you're playing some video game and the orientation of something just goes crazy, maybe they were using Euler angles and it went to one of those singular configurations. Numerically, something will a 1/0 will occur, and then you know, the computation stops. So you don't want that on a $200 million satellite. So there's sets of 4 coordinates that do not contain these singularities, but the coordinates are not independent. They're constrained by constraint equations. All right. So hold on. Let me draw. I haven't drawn any pictures. You're like, what's up with that? So the example of, let me say, yaw, pitch, and roll. So this is often used with aircraft. If you've got try to draw, this is Earth. Gosh, that's terrible looking. That's Earth. Okay, there's Earth, and there is a frame attached to the Earth. We could call this I'll use capital I, capital J, capital K. So this is the Earth centered inertial frame. And it's, right, the Earth is rotating with respect to this frame. So let's say this is the Earth-centered inertial frame, where we'll get into more detail later about what these directions are. But this is a set of directions that, as Newton would have said, are fixed with respect to the stars, the distant stars. He didn't think the stars were moving. We now know they are. But you've got a frame. Oh my goodness, I have an Earth here. Wow. I don't know if I'll use this much. There's green ones. Now I have a green screen here, so green countries just sort of disappear. So the Earth is rotating with respect to this inertially fixed frame. But this inertial frame is, think of it as centered at the center of the Earth and does not move with respect to the distant stars. And then we've got our spacecraft. And I don't know how to draw spacecraft. Here's a spacecraft. Looks like a box. And we'll put a frame on this. Actually, here's the spacecraft, and it's in some kind of orbit. Right. This is the spacecraft. I don't know what I was drawing there. Spacecraft orbit. Just a little piece of it. And often one will describe a frame for the spacecraft orbit, but right now we're just going to write a frame for the body. So suppose this is our box, and I'll use blue because I've got this blue frame. Suppose I've got I'll call this B1, B2, and B3. This is the frame attached to the spacecraft. So it's a body fixed frame thing. In the last minute, let me just say something about all spacecraft need an attitude determination and control system. This is often abbreviated as ADCS. It's not just spacecraft that need these. A drone that I will later fly today will need one of these. So there's math involved in the determination. Determination requires knowledge of kinematics. It's the math part. Technology is that determination requires sensors. That are up to the task of doing this. And then the control part in this attitude dynamic determination and control. Control requires knowledge of dynamics. And then the technology part is that control requires actuators. All right, and I know I've gone a minute over time, so we'll just leave it at that. This recording will be provided if you missed some part of it. I'll be continuing talking this sort of high level thing and then relating it to mission analysis and mission requirements next time. But that's it for now. So